My name is Amit Gupta. I'm a Senior VP and GM at Siemens EDA. I was founder and CEO of a company called Solido Design Automation. And Solido, we were focused on how can we apply AI to EDA? How can we automate chip design? And specifically, we were focused on custom IC design. So I started the company in 2005. Of course, large language models weren't available then, so we were using machine learning type techniques. I grew that company, and it was bought by Siemens in 2017. So I've been with Siemens for the last 8 years or so, and I run not just the custom IC business, but also the central AI team, which is servicing AI technologies and an AI platform for all the different products within Siemens EDA. So digital design creation, digital verification, hardware emulation, physical verification, OPC, board level design, as well as custom IC design. So what I'll be talking to you today is how specifically we see and we view AI as impacting chip design and impacting board design. But before I get into that, what I'm going to do is set a little bit of context. What are some of the trends that we're seeing in the industry? How is chip design growing? How's the semiconductor design growing through this fifth wave of digital compute? Then I'll talk about some of the challenges that are being seen by semiconductor companies in navigating this fifth wave of digital compute. I'll discuss really our focus in Siemens, not just at the EDA level, but more broadly across Siemens overall of developing out what we call the comprehensive digital twin. How can we emulate the design and the manufacturing and the in-field use of not just chips, but whole systems using a comprehensive digital twin? And then I'll get into the AI-powered EDA future that we're building out and what sort of AI innovations and technologies that we're developing. Okay, so first of all, getting into the fifth wave of digital compute, what are some of the trends that we're seeing in chip design and board design? And of course, these are famous quotes that we've seen. Marc Andreessen famously in 2011 talked about how software is eating the world, how software is able to disrupt whole industries. We saw Uber, for example, disrupting the taxi industry. We saw Airbnb disrupting the hotel industry, and having software be able to redesign the user experience and how we as consumers use these different industries. And then Jensen Huang, the CEO of NVIDIA in 2017, a few years later, famously talked about how software is eating the world, but AI is going to eat software. So what he was talking about there was really two aspects. One is in the design of software itself, using AI to be able to more productively create the software that's ultimately eating the world. And then secondly, at the application level, being able to have more AI in the user experience and having AI-first applications that are, of course, getting very quickly developed today. So these are kind of the macro trends that we're seeing in the industry. And then when applying it to the semiconductor market growth, there's been a few different revolutions. There was the PC revolution in the 1990s. There was the internet revolution in the 2000s, mobile revolution in the 2010s, the IoT revolution in the late 2010s, and now we're in the midst of the AI revolution in the 2020s. And what you could see is that the growth of the semiconductor industry has been growing steadily to be able to service all of this demand for these waves of computing, where by 2030, it's expected to become a $1 trillion market size industry. Now, zooming into AI itself, the growing appetite for data from AI is growing as well. So things going from Netflix recommendations to cat versus dog image recognition to AlphaGo to, of course, ChatGPT and AI agents to artificial general intelligence. This whole area of evolving the capability of AI is also driving the need for more and more data, and also the capabilities of these systems is growing. So overall, kind of the trend that we're seeing, the change is moving from this hardware-centric world where there was software that was adapting to general purpose hardware to more of a software-defined world, where software is providing all of the differentiation and automation capabilities in the system, and purpose-built silicon is driving these workloads, and of course it's being wrapped by AI. So what we're seeing is this growth in the industry, this growth of semiconductor demand is being driven by the need for supporting software differentiation as well as the AI within that software. And really this is moving us towards this software-defined, AI-powered, silicon-enabled world. Software-defined, again, providing all the differentiation in the systems, silicon-enabled to support those workloads, and AI providing the automation and the intelligence of these systems. And that's really what we're focused on within Siemens, is building out software and tools to support this next wave of development and growth in semiconductor industry. So that's a little bit of the context of what's happening in the world and what's creating this demand for more and more semiconductors and more complicated semiconductors. So now, how are companies navigating this fifth wave of digital compute with AI? Well, first of all, developing and designing these advanced semiconductor chips is becoming more and more complicated. Going to 2 nanometers compared to 5 nanometers, the amount of engineering hours required to make that chip has increased by about 55%. So there's a growing demand for engineering hours and requirements for engineering hours to get these chips out. A study done by IBS Design showed by 2030, there's actually going to be quite a huge shortage of semiconductor workers, semiconductor designers, semiconductor talent that's available. There's about a shortage of about 67,000 engineers by 2030 to be able to fulfill the demand for all the semiconductor design out there. And finally, the costs are going up. So estimated first-time total SoC design cost is about $300 million for a 3-nanometer node. So we have this world where there's more and more need for talent to be able to develop out these advanced semiconductor designs, but there isn't the availability of the talent, and the costs are going up. And then when you're looking at semiconductors as part of that silicon-enabled area that I was talking about earlier, there's different silicon needs across the different end markets, from hyperscalers to automotive to industrial to consumer electronics to aerospace and defense. There's different software-defined differentiation that's happening in each of these different end markets, and therefore different custom-built silicon to enable those kinds of workloads. So just the complexity of all this design requirements is going up and up. So the way we kind of break it down is looking in 3 areas. There's a system level complexity, the chip level complexity, and then finally the ecosystem level complexity, where at the system level you have to take into account all of these multi-domain systems. You have to look at the overall system reliability, the overall system efficiency. At the chip level, there's aggressive power, performance, area requirements that we need to achieve. There's saturation of transistor density on single chips. We saw, for example, the iPhone Air release that just happened, and the concentrations of chips in that kind of system, is incredible. And there's increasing complexity and requirements at the chip level. And finally, at the ecosystem level, there's tends to be a lot of different point tools in EDA, and being able to bring all those point tools together into a unified design data workflow, being able to put the data all in one place so that you can take advantage of the data. For example, if you're a designer, you want to see, okay, well, how did the chip perform in manufacturing? How did the chip perform when it was out in the field and being used by designers or by users? Being able to bring that data back into early design and be able to take advantage of that information becomes very important. So, at a high level, there's challenges at the system level, there's challenges at the chip level, and then there's challenges at the ecosystem level that we all need to solve. So what we're doing in Siemens in order to tackle this fifth wave of digital compute and the challenges associated with the fifth wave of digital compute is really building out the infrastructure and the capabilities for the comprehensive digital twin. And we see the comprehensive digital twin as foundational to the next generation of both semiconductor design and semiconductor manufacturing. So what do I mean by digital twin? So this is a simple example of an airplane, an airplane that's getting designed, getting manufactured, going out in the field. What's really needed is the ability to create the digital twin of that product, so that in software, in computers, you can be able to simulate, okay, this is the design of it, this is how it's going to perform when it's out in the real world, be able to do iterations in software to create that real world system, and then also be able to create a digital representation of the manufacturing so that we can make sure that the design and the manufacturing of that system is efficient and effective and with high reliability, high yield. So being able to create that digital twin at the design level and then at the manufacturing level before you do the real world implementations is what we mean at Siemens about the digital twin and creating that comprehensive digital twin. And what the other part of comprehensive is being able to account for all of the different types of modalities, all the types of multi-physics effects, all the types of domain of information that you're going to be able to have to consider. Things like, of course, semiconductor design that we know very well, but things like 3D IC integration, things like electronic systems, mechanical systems, air fluid dynamics, thermal systems, all of those different multi-physics, multi-domain effects, be able to consider that all in the context of that comprehensive digital twin, so you have the most accurate representation of how that system or how that chip will work when it's actually manufactured and it's actually used in field. So that's the focus that we have in Siemens EDA in the context of chip design and board design, creating that digital twin, creating that system anywhere from software to functional IC design and verification to physical IC verification to manufacturing to 3D IC integration and verification to putting it into the board for the whole electronic system. And there's a bunch of different areas of creating that digital twin, from AI to 3D IC integration to cross-domain analysis to cloud-based design to ecosystem collaboration to semiconductor lifecycle management. There's a bunch of different solutions that we're investing in Siemens EDA to be able to make that comprehensive digital twin a reality for creating chips and creating boards. But what I'm going to zoom into, and given that we're in the Samsung AI Forum, what I'm going to zoom into is specifically what are we doing in AI, what have we done historically in AI, and what are our investments going forward in AI to be able to realize that comprehensive digital twin vision. So that gets me to the AI-powered EDA future. And what does that look like? Well, first of all, the problem statement that I talked about earlier about going from 5 nanometers to 2 nanometers and the amount of engineering effort that's required to be able to design that chip going up by 55%. This was another study done by IBS Semiconductor, and what they predict is by implementing AI, the potential productivity boost is about 50%. So that's one way of closing that gap between the requirements and demand that we have from engineers and what we can actually deliver based upon the number of engineers that are graduating. Have AI be able to fill that gap, be able to provide a huge productivity boost to designers, to engineers, to semiconductor organizations to be able to design more and more without scaling the number of resources that they have available. So where are we investing in? And there's a lot of talk, obviously, now and a lot of implementation in the area of large language models for generative and agentic AI. And that's certainly one area that I'll be discussing today of how we're applying AI to be able to improve the productivity of chip design, chip manufacturing. But another area that we're making a lot of investments in is in the area of machine learning and reinforcement learning. Not everything is an LLM problem. A lot of the types of problems, the types of use cases, the types of tasks that we're addressing with AI is more conducive to ML, RL type algorithms, types of technology. So just wanted to illustrate the fact that there's a lot of different areas of AI, not just LLMs, that we're investing in to be able to improve the productivity of designers. And what we're finding, and I'll show you a demo later on in this presentation, is that we can create these powerful hybrid AI systems where you can have agents, large language models, be able to invoke tools that are using machine learning or reinforcement learning under the hood. So you're getting a multiplicative productivity benefit of agents working with machine learning to be able to ultimately get better designs out faster for organizations. And that's really what this illustrates is this idea of at the front end where the designer being able to input in through natural language, this is the kind of setup that I want, this is the kind of design that I want, this is the process node that I'm working on. I'm interested in migrating this design from 5 nanometers to 3 nanometers, being able to explain things in natural language and being able to have agents or generative AI systems then be able to call tools in the back end to be able to do tasks, do simulations, do verification type tasks, and then underneath the hood of those tools, having machine learning and reinforcement learning to be able to dramatically improve the productivity of the tools themselves, where instead of, for example, running millions or billions of simulations in brute force, being able to have the machine learning or reinforcement learning algorithms be able to build predictive models and be able to reduce the number of simulations down from millions or billions to hundreds. So it's this kind of hybrid system that we see unlocking a lot of power for our customers, being able to have this natural language interface with large language model-based design and having ML, RL under the hood. So having started Solido back in 2005, where, as mentioning at the beginning of this talk, our mission really was to apply AI to chip design, to board design using EDA tools, what we learned was when you're applying it in engineering type contexts, there's a lot of kind of unique requirements, a lot of unique attributes that are required by the AI. Things like verifiability. Designers don't want black box AI that just generates an answer and then you don't have any source as to, okay, well, why is this the answer that the AI came up with? So being verifiable is very important. Usability is really important. So not having to go to a separate window, a separate terminal, but having the AI where the designers are so that it's in line with where the engineering tasks are. Generality, being able to work across a number of different types of design, from SoCs to memories to analog designs to digital designs, being general to work across all those different types of designs. Robustness, so being able to work in these heterogeneous on-premise or within the secure data center type environments, not going off into the cloud and being able to preserve data security. And finally, accuracy, being able to have results that are brute force accurate, as if you ran a brute force simulation and you got the whole result. You don't want a result that's plus or minus 10 or plus or minus 20%, because then you can't sign off on those results. So in addition to speeding things up and improving productivity, when you're applying AI to EDA, these other types of attributes become very important. And that's where we spend a lot of our time investing into, is being able to create the attributes of these other kinds of capabilities in our AI. What else is important when you're applying AI to EDA? Being able to do things like expertise, so being able to answer questions of designers, being able to go into your data lake and being able to pull information from that to be able to act as a knowledge assistant for designers. Being able to accelerate design, so being able to do things like generate scripts, configurations, designs, tool automations, and finally faster verification. So being able to do things like speeding up test bench generation, speeding up verification tasks, those kinds of things. So those are three broad categories of expertise, accelerated design, and accelerated verification that we need from our AI systems. Another important part of applying AI to EDA is that, of course, in EDA, in the context of chip design, board design, there's a lot of different modalities compared to the traditional modalities of large language models. There's RTL, there's Verilog and Netlist, there's GDS2, there's Liberty files, simulation data, schematics, waveforms. So there's all these other modalities in EDA that the AI systems need to be able to understand and process compared to just the traditional modalities of large language models. What else is important when you're applying AI to EDA? Being able to have a system that scales with the increasing capabilities of the GPU compute. Being able to scale with the increasing capabilities of the large language models, and be able to scale with the increasing capabilities of the services that are being provided through the various frameworks and open source capabilities that are out there. So being able to take advantage of all this innovation that's happening at the infrastructure level and being able to essentially be the translation layer to applying that to EDA, applying that to chip design and board design. What else is important when applying AI to EDA? Being able to work across that whole workflow, from software to functional IC to physical IC, all the way to board electronic system type design, being able to power that with AI and being able to provide productivity benefits and efficiency that way. So kind of the three general buckets that we talk about for applying AI to EDA is scalable intelligence, so being able to tap into a centralized multimodal data lake for design or manufacturing data for semiconductor, hardware agnostic deployment, support for multiple LLMs. So some LLMs might be good for reasoning type tasks, some for more Q&A type tasks, some for more agentic type tasks. Being able to support your LLMs, so if you want to fine-tune LLMs based upon your own data, being able to support those kinds of things, and not just be limited to large language models, but also machine learning and reinforcement learning capabilities. Another area that's very, very important for semiconductor design is being secure and customizable. So being an on-premise solution or supporting cloud within your own secure data center, having that enterprise-grade security. Often in our world, there's access control limitations where certain designers, due to export control, have access to certain data. Other designers have access to other data, and you don't want these large language models or these AI systems to give access to designers to data that they don't have otherwise access to. So being able to honor those access control privileges that organizations may have in place. Ability to build these custom workflows and also connect to other AI systems. Oftentimes we see companies build out their own internal AI systems that has a repository of information and internal knowledge. So being able to take advantage of that and be able to leverage that when applying AI to EDA. And the third kind of major bucket is user-centric design. So being available through the GUIs of the tools, the command line of the tools, through web interfaces, through really wherever the designers are, and being able to take advantage of this data flywheel effect, where as companies are using the AI more and more, data is being added to this data repository, to this EDA data lake, so that the AI can take advantage of learning as it's being used. So constantly getting better and smarter as it's being utilized more and more. So what we've been working on over the last really 2 decades is kind of a few different areas. One is what we call adaptive AI. So using machine learning to be able to build these adaptive AI models and be able to do prediction, and I'll give you a couple examples there. Additive AI, to be able to reuse AI models between different runs for chip design. Internal AI, where the AI is embedded into the solvers of the different engines, like simulators, for example. And then finally, generative and agentic AI, being able to use large language models to be able to improve the productivity of designers. So first of all, for this adaptive AI approach that we use, what's interesting with applying AI to EDA is that it doesn't really make sense for you to build these predictive machine learning models that are generic, because it's a function of the design that you're doing, it's a function of the measurements that you're doing, it's a function of the PDKs that you're working on. So the approach that we've taken for machine learning is to be able to create training data for the machine learning on the fly as the tools are being run, and being able to infer from those AI models adaptively, and then based upon comparisons with golden data, be able to tune those AI models at runtime to be able to ultimately get the results that the designer uses. So kind of the flow is an initial design of experiments where some of the points are simulated with golden brute force accuracy, and then a initial machine learning model is built to predict the outcome. So the example that I'm going to show here is being able to verify a design to 7 sigma. So 7 sigma means that there's only a 1 in tens of billions failure rate of the chips. So what the designer wants to do in this case is be able to predict out, okay, well, what is the performance to 7 sigma? Am I going to be able to achieve my specifications to 7 sigma? So what the machine learning adaptive AI technology does is it creates this AI model based upon some initial design of experiments, and then it starts predicting out, okay, well, what does a 7 sigma performance look like of my chip? And what it will do is it'll do some prediction in those 7 sigma regions, and it'll drive the simulator, the golden accuracy engine, under the hood to be able to compare what the predicted result is versus the actual golden result. And based upon that information, it could feed back and tune that AI model on the fly in real time until it's able to accurately predict those tail regions and optimize that model, kind of having this feedback loop of adapting the model as it's getting more and more information. The other interesting thing is that it can show to the user, okay, this is how I've come about solving this problem, and it can expose all that information to the user so that there's more verifiability. One of those attributes I talked about earlier that's very important when applying AI to chip design and board design. And finally, knowledge extraction. Because you've built this ML model, you have all the information in terms of sensitivities, and you can provide a tremendous amount of insight to designers as to, okay, well, it's these transistors or these transistor parameters that are causing the sensitivities and causing the design to not work at 7 sigma. So there's a whole knowledge extraction step that's available. And here's an example, a screenshot from one of our tools of this in action, and you could see the goal was to verify the design to 7.1 sigma, so that would be the equivalent of 10 trillion. I was wrong earlier. It's actually 1 in 10 trillion, or 1 in a trillion failures, so you would need to do about 10 trillion Monte Carlo analyses to be able to verify this brute force. But using that adaptive AI approach that I just went through, you're able to verify the design to 7 sigma in only 4,000 simulations. So massive, 2.5 million x or 2.5 billion x faster number of simulations, going from 10 trillion down to a few thousand simulations, all with perfect accuracy to be able to do the verification of the design. So really, powerful example that's now widely used in the industry for verification of designs to higher sigma. Another example of our AI technologies is what we call additive AI. So instead of building that ML model on the fly each time, be able to reuse the AI models between runs and be able to verify automatically, okay, does this AI model still apply? You know, the process boundary changed, or the measurements changed, or, you know, my transistor sizings changed. So being able to figure out through simulation if that AI model is still valid, and then if it is, being able to reuse that AI model, we're seeing, you know, speed ups from 2x to 30x fewer simulations by being able to reuse those AI models. So that was kind of all in the realm of machine learning, reinforcement learning. What we're also investing in Siemens EDA is how can we use large language models to be able to dramatically improve the productivity of designers. And we launched at the Design Automation Conference our new EDA AI system that we call Fuse, to be able to speed the design of semiconductor and board design. And we also launched some AI capabilities within our digital design creation platform for place and route, within our physical verification tools, and then within our custom IC analog tools as well. So our Fuse generative AI system enables these generative and agentic AI capabilities across the whole Siemens EDA tool workflow. It has that data flywheel effect, so the more you use it, you're able to save that information into the central AI system, or the central EDA data lake within an organization. It's fully secure, so it's an on-premise solution. None of your data is leaving the organization. And finally, it's open. So we expose the APIs, so if you want to infuse your own data, or if you want to build your own applications on top of the Fuse Siemens EDA AI system, that's also available. And this is what the Fuse Siemens EDA AI system looks like. It has the large language model layer, which we can use our own foundational models on, or you can bring your own models. It has the multimodal EDA data lake that points to different data sources, things like manuals, examples, glossaries. We use retrieval augmented generation within the system. You can also insert any fine-tuned models that you may have. And the types of use cases that it enables are things like assistance, being able to do Q&A on questions that designers have, reasoners that do human-level problem solving, and finally agents that are able to call tools and invoke various tasks. And that's integrated completely within the Siemens EDA tools. So whether it's our Salido custom IC tools or Calibre physical verification tools, Tessent design for test tools, and so on, the Fuse Siemens EDA AI system is enabling, empowering these generative and agentic AI capabilities. Something also that we find really important is making sure that the AI is where the designer is. So whether it's in the GUI of the tools or the command line of the tools or in a VS Code editor, for example, or a cursor, or in Slack or Teams, you know, being able to talk to the AI and be able to get the knowledge, be able to do the design, be able to get those verification speed ups that I was talking about earlier. We're partnered with NVIDIA on this as well. So with NVIDIA, we've built out using the NVIDIA NIM microservices framework, as well as the Llama Nemotron we support. So if you want to use kind of an NVIDIA ecosystem, we support that, but then we also support non-NVIDIA ecosystems as well. And there's the whole capabilities around assistance to be able to quickly answer questions that you may have about your design or the documentation, reasoners to be able to do this multi-step thinking and analysis, and then agents to be able to do natural language tool calling to be able to speed up various design and verification tasks. And this is an example of how our AI agents work, where you put in your input prompt in natural language, and then the large language model with the memory, with the agent persona, is able to have all the context of this is a tool that you're working on, and this is how to be able to speed up the kind of tasks that you want to do, whether it's a setup kind of task or a report generation type task, or a log file analysis type task, the various tasks that are done for design and verification. So we've really kind of focused on this wave one of AI agent building. And what we're starting to invest more in is wave 2 and wave 3, where wave 2 is specifying more at a higher level. This is the kinds of designs or the kinds of tasks that I want to do, and having the autonomous agent be able to put together whole workflows and be able to drive tools, not just one tool, but multiple tools to be able to drive that workflow. And then wave 3, having multiple instances of AI agents or agentic AI workflows to be able to do many design or verification tasks in parallel. So, for example, looking at a physical IC verification type task, wave 1 would be something like analyzing the design rule check violations that might have existed and be able to look through the log files. Wave 2 is planning or completing this full RTL to GDS2 flow using little human interaction or supervision. And then finally, wave 3 is being able to do multiple RTL to GDS2 types design. So wave 1 is where we're at right now and providing a lot of capabilities, and have started making investments into wave 2 and wave 3. And taking an example in the context of custom IC design and verification, because that's my area, what we're building out are agents for all the different tools that we have. So Slido Design Environment is a simulation environment tool, so we have the product agent for that. Slido Simulation Suite is our simulator or SPICE simulator tool, so we have the agent for that. Slido Custom IC Design Agent does all the schematic capture and layout of the designs. And then we have kind of the master agent that's able to deploy tasks, calling the various product level agents, and be able to work between the different agents to be able to complete whole custom IC design or verification type use cases. You could see the power of how we're doing what we talk about as this hybrid AI, being able to use natural language for designers to very quickly be able to set up the design, run the tools, debug problems that come up inherently, be able to generate reports, be able to provide the orders of magnitude speed up at the front end, as well combining that with the machine learning and reinforcement technology that we have under the hood. So there's a whole value that we are creating with AI across the whole work stream, from design creation to verification, optimization, workflow, process automation, engineering focus and impact. And I actually asked Google Gemini, what's the impact of AI for EDA? So these are the results just from the AI telling us how AI can help EDA. So, and I thought it captured it quite well across all those different design stages. So that's really how we view things and where we're making our investment. We see AI as being a multiplicative productivity improvement for engineers, whether it's through natural language at the user level or under the hood of the tools. Using AI across all of our different types of tools in Siemens EDA, and really enabling that comprehensive digital twin that I talked about, being able to create these comprehensive digital twins from systems down to chips that, of course, we're focused on. So, and the types of value that we're delivering already with AI across all of our different tools, from digital to analog design to verification, these are the types of value points that our customers are already seeing. That's the focus that we have in Siemens. Thank you very much.